Hi, everyone, and welcome back to the Regression and Beyond series. In this video, we're going to be talking about sample size planning and power analysis, or in other words, things you'd be doing before you actually conducted a study. Typically, we think about this for primary data collection, but you could also do a version of it for secondary data analysis. And what I'm going to run through today is essentially drawing on a tutorial paper that I'm citing, have the DOI at the top of the file here, and then applying a Muthen and Muthen's approach. So specifically, commonly you'll see when people do like power analysis or something like that, often kind of one of the go-tos is something like G power. But in this video, we're going to talk about using the Monte Carlo method or conducting simulations to not only look at power, but also other questions we might have, like are the parameters or standard errors going to be biased? Now, we won't have to import any data because we're going to be simulating things. So at the start here, you may need some packages, the simsem package, and then snow. That's potentially only applicable for certain types of computers that you're operating on. But basically, it's going to make, because we do thousands of these, often it's going to make things go a little bit faster if your computer has the kind of capabilities for it. So the approach that we're going to implement here makes things pretty straightforward. At some point, I might show kind of more the nuts and bolts of kind of simulating data, but this one makes it relatively straightforward because it uses, or the version that we're going to approach is using Lavaan. So we've used Lavaan for things like latent variable models. You can use it for multi-level models, these types of things. Most commonly, I would say for latent variable models. But this approach just draws on that. So we're basically going to set things up as you would in Lavaan, as you'll see, which makes things a little bit more straightforward. Now, the main things we want to, or I would say typically you want to figure out at the beginning before you start any sort of power analysis are basically going to be kind of your key decision rules, like a basic one, some sort of alpha level, right? If you're going to have a 0.05 is typically a really common one. You might set also your desired power. Again, common heuristic for that is 0.8, but you could set this at whatever you wanted. So in this case, we're going to assume those things. We're going to assume the 0.05 and generally assume that we want a power of a point of about 0.8. And we're going to keep things relatively simple and straightforward in this one, but everything will walk through. There's natural extensions, and you can make this more complicated for your specific circumstances. But we're just going to talk about here basically a simple linear regression model that you might want to run, and we're not going to deal with potential complications like missing data or potential sharp deviations from the assumptions that we might be making. So outside of assumptions like what's our alpha level that we want to do, we're also going to make assumptions like the effect size. So if we think, that X is going to have an impact on Y, say, okay, well, how big of one? And here again, we run into some heuristics about kind of what's a small, medium versus a large. So there's some general heuristics that you can follow. Ideally, or an ideal world, there are going to be kind of a bunch of studies or a meta-analysis that you could go to and say, okay, I have a really good idea of, I think roughly the standardized effect size is going to be about this. In this case, we're going to assume broadly what you'd call, or many people would consider, a medium effect size, or roughly a correlation of 0.3. And the question we're going to start off with is, okay, how big of a sample would we need if we want to look at this relationship between X and Y, and given all the assumptions that we've set up? Well, the first thing we start with, again, mirroring using the Lavaan syntax, and I think I forgot to actually load the packages. No, simsem loads Lavaan automatically. But using Lavaan syntax, you might remember, generally we specify the model first and then we fit it second. So similarly here, we're going to use a similar process, but the first one we're going to start with is what we're going to assume kind of our population looks like. So in the population, if we assume there's this relationship between X and Y and it is this specific size. Again, I'm specifying that here with the 0.3 times X. So I'm fixing that relationship. So in this population, and in this case, I'm not including anything else, but by default, we're going to assume these are normally continuous, normally distributed variables. Again, you can modify that, but we're going to keep it pretty simple. So first, we would, again, just run that. Nothing's going to happen because that's just what we're specifying. The next part of it, we can think about now if we were going to grab like a random sample from that population and actually conduct an analysis like we typically do or is commonly done with studies, and then estimated this model of Y regressing on to X. That's the model we want there. So again, basically looking the same at this point. Only difference is one is 0.3, and this other one, we don't specify a specific size of the relationship, just like you would, again, if you're imagining you were going to do this study and you did get a random sample, right? You would be estimating this relationship. So population, we assume we know what it is. Here, we're just specifying like you would in a typical regression model. Now, again, I'm going to kind of walk through the approach that Boygene, I believe is how you say the name, generally walks through kind of the tutorial approach. Again, not any kind of hard and fast rules about this, but I think it gives a good kind of starting point and basic approach. So what are we doing here in this next part? So first, what we're going to do, again, you see we're specifying that analysis model. So that's what we're going to analyze, right? That's the regression. And here, remember, at starting point, we want to figure out kind of what sample size we need in order to specifically, we're going to look at kind of minimize bias and have the achieved power that we want. So here, what we're going to do from that population that we specified, we're going to take some random samples. We're going to take a sample of 100, 200, 300, and then we're going to do that basically over and over again. We're going to do that 100 times. So that's what this is specifying. Again, with the idea, if it were true, what we think is true and the population does look like that, and you were going to do a study, what would you expect to find? That's basically what we're getting at here. So the generating, this is the actual population model again, so the population data that we're assuming. This is just a quick connection to Lavaan, because we're going to be using the SEM command there. The seed, surprisingly important, because as much as we want to try to capture, a random sampling approach, we're basically just trying to mimic randomness rather than perfectly capture randomness. So setting the seed value can be important, and we'll talk about that a little bit later. You often want to change it, but if you want your results to be consistent, you have to use the same seed value. This multi-core, this is going to be for multiple processors. This is where that SNO package came in. Again, it might not work on your computer, but if you have a relatively computer, purchased in the relatively recent years, you probably will be able to do this. So now I do that. Doesn't look super exciting initially. One thing I'll note, if you don't have the multi-core, we'll get kind of an updating thing down here. But when you do have the multi-core, we're not going to update. You would just see a stop sign up here if it's running. So now let's look at the output. That is what this command is doing here. Just a summary. So again, we did in sequence, grabbing different sample size. We're trying out to try to figure out what might be a plausible sample size. So generally, methane and methane lay out these three criteria. I think broadly there would be kind of good heuristics to use for a general approach. And again, while we mentioned sample size planning and power analysis, broadly we're interested in other things beyond bias. So you'll see here that a lot of our kind of criteria actually are focused more on bias than anything else. So parameter and standard error bias, we want to be basically small. Standard error bias, especially for any parameters, that we're like theoretically interested in or making some hypothesis about, and then our coverage. So these are the initial kind of three criteria before we even ask that question of do we have power. We're actually focused broadly more on bias first. So here is the kind of breakdown of what the actual calculations are. When I'm saying bias, what do we actually mean? The core of it is we're just taking the difference between all the simulations we did, again, so taking those random samples, estimating the model, and then seeing what we get. If you do that over and over again, like we did, on average, what does that estimate look like versus what we assumed it? So remember, we assumed it to be 0.3 for the essentially for the coefficient specifically in this case. So it's basically, is it 0.3 or is it different from 0.3? And then we're just basically turning that into a proportion. Standard error bias, similar idea, right? Versus the assumption versus what we're getting across these simulations that we just repeatedly did. And then finally, coverage is essentially the confidence interval. Are the values actually falling within, again, in this case, assuming a 95% confidence interval? Within that assumed one, when we do all these simulations, all those estimates are 95% of those estimates actually falling within that 95% confidence interval, which is what we typically assume. So again, we just did like 100 simulations there, so things can, you can get a decent amount of variability, and we varied the sample size. As we'll see in a second, often we want to do thousands of these simulations. So again, for now, we're just kind of trying to figure things out, like what's a plausible kind of sample size. And based on what we kind of just looked at, we could say, okay, roughly we're kind of in a decent territory. So if we go back to look at this one, the explaining these column names, because some of that output can be a little bit confusing to break down. But this is going to be the parameter bias here, the rel bias. We want that less than 0.1. Then there's the rel SE bias, or relative standard error bias. That's going to be our standard error bias, which we want to be less than 0.05. Again, for our focal predictors, in this case, we only have one. So if we look at that, just above 0.05, and then you look at coverage, and basically, is it aligning with that 95%? So based on that, we're pretty close. But again, if you look at that relative standard error bias one, we're slightly off there. But again, we're suggesting, given what we just ran, we're somewhere in the territory, right? Somewhere between a 100 and 300 is probably where we want to be. So let's try this out, and we'll do a sample size of 200 now. So again, basically the same line. We just had the n equals 200 there. So that will take a second to run, depending on your computer. It might be faster than mine or slower than mine. Take a sip of your coffee. And here we go. So now if we jump back and want to look at things, our rel bias, remember, we want it to be less than 0.10. Rel SE bias, we want less than 0.05. So we got that. And then we already knew coverage was in a good spot, but looking at, again, we're still in a good spot. We want it at 0.95, and we are at 0.95, exactly where we want it to be, close to 0.95 basically. And we're almost exactly right there. So now it's looking pretty good. We hit those criteria. So we'd expect to have largely unbiased or not severely biased estimates if we were going to conduct this study and our assumptions are true. So the next thing we want to look at is power. So here it's going to be across these simulations that we did for which proportion did we get p-values that fall under our assumed alpha level. So again, traditional 0.05, this is going to be how many times across these simulations we got a p-value less than 0.05. Now, again, the basic idea is we want to get generally the heuristic is around 0.8. And if we look at ours, oh, wow, we actually have a high degree of power. So if it were true, as we have set it up, and it was true, and we were going to do this study and then regress y onto x with a sample of 200, we would have the power to detect that effect. Now, overpowered study, not inherently kind of wrong, but especially if you're thinking about primary data collection, right? If you had to pay for the sample size, right, you might start getting the question of, oh, okay, maybe we can get away with fewer people. So just to work through that process, let's try that out. Again, everything is basically staying the same here. I'm just changing that sample size to 150. And again, I'll take a second to run. And we did it. We ran through. So all the criteria, again, were still met. If we look at this, the rel bias, rel SE bias, coverage still looking good, not exactly 0.95, but we're still pretty close, and power still looking pretty great, still above 0.9. So now let's, again, just keep going through it. Like in the process, you might do this kind of process. And okay, let's see, maybe we'll do a little bit smaller. Maybe we can get away with 100. And while we're waiting for this, I'll kind of foreshadow. But essentially, with that sample size of 100, all the criteria are met, and we're going to get power that's close to that generally accepted heuristic of a desired of about 0.8. So, what would you do at this point? Well, as I mentioned, generally you want to bump up the number of simulations or replications that you're doing. And again, we have the output going here. I'm going to run this next one while I'm talking, and hopefully we'll get there. But this one could take a decent amount of time, especially as I'm recording. Might go faster on your computer. But generally at this point, if you kind of figured out, okay, this is looking like a good sample size, what would you do next? You're going to bump up the number of simulations, replications. General rules, at least 5,000. You might do 10,000, sticking with the 5,000 here just for the sake, and you're going to want to rotate around the C values. So again, you'll see that here. I changed the C value, and then I also increased to 5,000. So generally wouldn't expect things to be radically different at that point, or that's what you would hope. But this is basically just a general check for that. Things are going to be more consistent and stable the more simulations, replications that you do. So in this case, to kind of spring forward, even though we don't have the results popping up just yet, this is something that we could use to justify, then say we're going to do a survey, we want to do some study and collect data from like 100 people or something like that. But even though technically you could argue maybe we're a little bit overpowered with a sample of like 150, you could also argue, oh, we're worried, okay, we might have response rate issues or something like that, or some amount of missing data. So to try to hedge against that, we're going to collect 150, even though 100 would be, technically adequate in terms of power and unbiased results. Now, what I want to turn to briefly next is that you can also do this process with secondary data analysis, though it's not always, I would say, or maybe just not as common, maybe, or at least in my personal experience. So could be different, but generally speaking, we often don't think about it because often with secondary data analysis, the kind of sample size might be fixed, right? But power analysis and actually thinking through these things, like will there be potential bias in parameters and do I actually have enough power to detect these things, actually can be quite useful, I think, with secondary data analysis. It might guide things, if you're interested in a whole range of variables, maybe you don't have enough power to look at all those variables, or things will get biased if you look at all those variables. Another thing, generally with interpretation type elements, secondary data, if the sample size is the sample size, you can't really do anything about it. But that doesn't mean that it's not, maybe tapping into some real world thing. And you could potentially report, okay, yeah, the power, not quite perfect, but it maybe can aid in your interpretation. Is this potentially biased? How accurate is it? So working through this quick example, again, another hypothetical. Now we're going to say we have two hypotheses, but we're going to work through this kind of similar process. Now you'll see, but we're mixing things up just a little bit. So not only two independent variables, they also have different effect sizes. Again, I'm starting to introduce this idea of you can start customizing pretty much everything that you would want. But the same process, so we're going to say in this, the population, right, in the one we're interested in drawing conclusions about, there's these two relationships for X1 and X2 and Y. And then we were going to do a study and maybe repeatedly do this study over and over and over again with random samples. What would things look like? Are things going to be unbiased, and would we have power? But again, introducing, it's not just often, I think, when people talk about power, these types of things, they maybe just overall model, or like we have the power to do this thing. But, power is going to be specific to each specific kind of parameter or hypothesis that you are interested in, right? You can have power to detect, one potential effect, but not another effect, or potentially the degree of bias in one parameter that you might expect to be really high, but then it could be really low in another parameter. And all that information, could be really informative. So now we got the output, and basically along the lines that I was hinting at, that's basically what we see. The criteria met, but you see with that X2, the one that we would generally consider something like a small effect size or a correlation of about 0.1, you see, even with a sample of 300, we do not have the power to detect it. Based on the design we set up, we actually know, right? We know there is this true effect, but if you were going to take something like a random sample of 300, and then given all these assumptions, like use an alpha level of 0.05, walk through that approach, you wouldn't have the power to detect it. Or otherwise, you would fail to reject the null hypothesis, even though it is false in this case. So again, adding into that interpretation, I think even more broadly, when you think about things like p-values, when you say like, oh, if it's a p-value of 0.6, okay, it doesn't exist, or it's not real, or something like that. It's entirely possible that there can be some real relationship, for example, between two variables in a population, and you could still have even a decently well-designed study, failing to reject the null hypothesis, despite there being some sort of real-world relationship. Hence, kind of tying into a lot of these things, why many folks are not super excited about how much we rely and the specific ways that we use p-values. So kind of ending here on some quick notes. Obviously a very kind of simple introduction. You can get really excited. You can, again, kind of customize this any way. You could do more different types of models, like generalized linear models, and then build in different assumptions. You can make different assumptions about variance, right? Maybe not just the relationship. You can build in missing data or violations of assumptions, all sorts of fun things that you might want to explore and say, hey, is this going to like potentially affect my model and my analysis? So if you're interested in exploring more of the specifically the simsem, which makes this kind of process pretty easy, you can check out their website. It has some fun vignettes that you can explore and that are really helpful. And then I think maybe down the line, I might do a video of maybe a little bit more nuts and bolts, and how you can kind of fully design your own simulation beyond, relying on the simsem package. Other one kind of related note, again, relatively simple, but note that we didn't include any sort of association between our independent variables in that model when we added that in. But that's definitely something that might want to, or perhaps in some cases, it's actually really important that you consider a potential association between your independent variables. So again, note you can build that in, and you can also build in a variety of other things. But this is just kind of a simple, straightforward introduction, and I hope it kind of familiarized you with the basics, and that you can use it and kind of apply it to your own situation. All right, thanks, folks. See ya.